Digital and Computer System Architecture Lecture, Lecture 1, Part 5, Bandwidth versus Latency. Okay, I'm your professor, Professor Hang Liu. So today's lecture is really about the involvement of computing technology and underneath that, the performance and the computer architecture impacts about it. So let's talk about 4 technologies about bandwidth and latency, okay? I believe you guys have already reviewed the reading material of bandwidth and latency. These two are very, very popular metrics we typically talk about, but people get confused about what is bandwidth, what is latency, okay? So we talk about 4 technologies of bandwidth and latency difference. That is disk, memory, network, and processor, okay? We compare them over time. So first, we do a little bit of summarization about what is bandwidth and latency, and we require all the students to understand them fully before you move on to next slide, okay? So bandwidth or throughput, they are typically mixed, like bandwidth and throughput. They measures the total amount of work or number of workloads that was carried or performed in a given time. The time is given, is static, and in that specific time frame, how many work you finished, okay? The latency or response time, they are also typically reused, interchanged. Means the time between the start and the completion of a single event, okay? The first one is given a time, how many events you are finished. The second one is you measure the time of a single event finished, okay? We will see that bandwidth and throughput are actually improving much faster than latency, okay? Starting from the disk of the old last gig versus the new fungal, right? So we see in 1983, which is pretty much 30 years ago, right? So we see that the RPM, so maybe you don't know what is RPM. Oh, good. If you know that, that'd be good. So RPM means rotate per minute. So we say this is very important for latency, right? So the capacity of the disk starts from 30 megabytes to 73 gigabytes, right? So it's like thousands of times improvement. Tracks per inch means the density of the data. It's like 800 to 64,000. It's 80 times. And bits per inch is also density. We have 46 times improvement. Number of platters. Number of platters means the capacity, right? How many platters? More platters typically means more data. Okay, we see the bandwidth improvement clearly is significantly more. It's improving from 0.6 megabytes per second to 86 megabytes per second. It's 140 times improvement. Excuse me. So the latency actually is reduced only from 48.3 milliseconds to 5.7 milliseconds, so 8 times. Why? Because latency pretty much is related to the rotation per minute, right? Well, bandwidth can be related to the density, right? If you have so many data packed together in a very small area, I can carry all of them out, and also I can improve the length. You can imagine the case of since we are in Hoboken, very close to Holland Tunnel and Lincoln Tunnel. So The latency is that the time of a single lane from the Jersey side to Manhattan side, right? So it's that is very hard to improve unless you can make the highway even faster or you have a faster car. But without changing the speed of latency, we can always improve the bandwidth by building more tunnels, right? Building more bridges. So that's what we're trying to say by the difference of latency and bandwidth. Bandwidth is easy to improve, while latency is hard. Okay, so if we put those things in the plot, we see that improvement of latency versus improvement of bandwidth is always lean toward the improvement of bandwidth, right? Okay, second, memory of archaic to modern, right? So we say from 30 years ago, per chip is around 60 megabits. Okay, right now it's 4,000 times more, like 256 megabits per chip. And then the number of transistors, it's a lot more, right? So from 64,000 transistors of 35 millimeters to 256 billion transistors of around 7 times more. So, but the difference of the number of transistors is a lot more. So the density is much higher, right? And the bus, this is the same as the Holland tunnel thing, right? So if you have more bandwidth, like the wider bus, right, from 16-bit data bus per module to like 64-bit, and number of pins is also more, like the length of the tunnel is also more. So then we have this 13 megabytes per second of bandwidth. This is exactly bandwidth. We say the bandwidth improvement is around 20 times, right? From 13 megabytes to 1600 megabytes per second. The latency improvement is literally same, like 4 times of like disk is 8 times, right? So we plot this memory together because disk improvement is 140 versus 8, while this one is 180 versus 4. So memory is even more lean towards like bandwidth improvements. Okay, then we go to the network, right? Network from like 30 years ago, 1978, actually even older. We see the throughput is 10 megabits per second, while in 2003, also 15 years ago, like almost 20 years ago, right? That is 10,000 megabits per second. That's a lot more, like 1,000 times more. Latency improvement is only 15 times. Okay. So we plot this together. We see network is also lean towards bandwidth. Okay, CPU, which is the key focus of the industry, as well as our course. We see here 1982 of Intel, 8286. The frequency is 12.5 megahertz, 2 million instructions per second. Latency is 330. And then for 2001 Intel Pentium 4, the frequency is 1500 megahertz. And we have 4,500 million instructions per second of peak. That is like thousands of times more, right? Latency improved from 300 of 20 to 15. It's like 20 times. And then the number of transistors, it's from 134,000 transistors of 47 millimeter area square to like 42 billion transistors of 217 millimeter area, right? And the data bus or the bandwidth related stuff. So it's a 16 bits data bus of 64 pins to 64 bits data bus of 432 pins. So that's much more, right? And other things like dynamic translation to RISC, super pipeline, out of order execution, all those things are improving what? Throughput. Like out of order makes more instructions to go, but every instruction probably even takes longer time. And actually we're sacrificing the latency for the bandwidth. So the left side you see is the layout of the 1982 Intel Pentium, Intel 2286 CPU of this one. And the right side is 2001 Intel Pentium 4 processor, right? You see significantly more transistors at PAP and more complex layout here, okay? If we drop the CPU here, we see the plot is like this, okay? The processor goes even higher of the performance than other things. So we see in total latency lags behind the bandwidth. Why? We have like a couple of rule of thumbs. In the time that bandwidth doubles, latency improves by no more than a factor of 1.2 and 1.4, right? And the capacity also improves faster than bandwidth. The stated alternative is that bandwidth improves by more than the square of the improvements in latency. Okay, that's the observation. Why? So first, Moore's law helps bandwidth more than latency. Okay, if you still remember our first lecture, we give a little bit of brief introduction about Moore's law. We're gonna definitely give a very detailed, like description about Moore's law lecture 2. So right now I give you a brief review. Is that Moore's law means what's the portion of the instructions can be parallelized? Okay. So if you have more portions to be parallelized, you essentially have more bandwidth, right? Fast transistors, more pins helps bandwidth. Well, does not help latency, or relatively. Only smaller, faster transistor, but communicating with longer line actually limits the latency, right? So imagine you have more transistors packed, then it's likely that you have longer communication path because you have to go across so many packed transistors. Okay. And then distance limits latency, right? So latency is the distance divided by speed. Okay. If you have that distance, then you cannot go beyond the speed of the light. That's what we're trying to say here. Well, bandwidth is easier to sell, right? So in today's market, in like let's say in the cell phone market, when we say we have 5G or 6G, typically the latency is not big difference, but the bandwidth is like double, triple, 10 times more, 100 times more, right? So the customers paying attention to, like for example, let's say we see the latency is reduced from 10 microseconds to 5 microseconds, versus it's the Ethernet is from like 1 gigabytes to 2 gigabytes. We feel okay, latency doesn't matter because my reaction is like that. It does not go below like certain milliseconds. Then I really don't care whether you get even faster or not. But if you have more bandwidth, I can transform my data, right? So that's something we typically keep in mind. The fourth point is latency helps bandwidth, but not vice versa, right? So bandwidth equals like the total data divided by latency, is it? Right, this is a given latency. What's the total transfer? So if you have a shorter latency, smaller latency, you help the bandwidth. But as what we mentioned, if you pack more transistors together and have more pins, that typically hurt the latency because you have introduced a longer distance of communication. So we say latency helps bandwidth, but not vice versa. See, this is the fifth point, right? So bandwidth actually hurts latency. That's what we mentioned about. And another thing is we have a layering stuff, right? So if you remember, we have the algorithm, application algorithm, and then programming language, compiler, operating system, architecture, instruction set architecture, microarchitecture, RTL, gates, logic, devices, electronics. Those kind of layers from one layer to another layer or operating system, those things hurts latency because you introduce so many passes from one step to another staging, right? So those things actually hurts latency more than bandwidth because you can always stage in more data together to amortize the overhead. So, but for a single event, the overhead is determined. Summary of technology trends. For disk, LAN, memory, and microprocessor, bandwidth improves by square of latency improvements. Or we see in time that bandwidth doubles latency improvements only by no more than 1.2 or 1.4. It lags behind, probably even larger in real systems as bandwidth gains multiplied by replica of components, right? You can multi-core, thousands of cores, and all the cores together is the bandwidth. Hardware software developers should innovate, assume latency lags behind bandwidth. If everything improves at the same rate, then nothing really changes. When rates vary, requires a real innovation in order to bridge the lag behind, right? Okay, can you use 15 minutes to find out real world applications that only care about latency? Okay, I know people care about pay a lot more attention to bandwidth, but can you help me to identify those outliers, some applications that really care about latency? I give you a hint, like driverless car, okay? Okay, so thank you for the discussion. For next lecture, we're gonna really go to the chapter 1. Please spend your time, read the entire chapter 1 before you review these videos. I'm Han Liu. Thank you for attending this class. Let me know if you have any questions. I'm looking forward to see you next lecture.